Good morning, grade 11s. In our last lesson, we took a look at what it meant to be a solution. What I want to do today is take a look at how solutions are made, how they form. I want to consider solutions made in water. We can use lots of different solvents to make a solution, as we discussed in our last lesson. But in today's lesson, I specifically want to talk about solutions that are made using water as the solvent. Water is a polar molecule. Take a look at the Bohr diagram showing the bonding in water. You can see that oxygen has these unpaired electrons, unbonded electron pairs, I should say, that are on this end. And that's a lot of negative energy there. Hydrogen also has a much lower electronegativity than oxygen does, and so hydrogen's one electron is actually being pulled quite a bit closer to oxygen's. Now, for both these reasons, when we look at a water molecule, the oxygen end looks a little bit negative, and the hydrogen ends look a little bit positive. So this little symbol here is the lowercase letter, Greek letter delta. It kind of looks like you're drawing the letter S, but closing it up at the end. It means it looks a little negative, and you'll see us use this symbol for polar molecules, because it's not all the way negative like an ionic molecule. So water has a positive and a negative looking end, and that's what allows it to be so good at dissolving things. So the process of dissolving is called solvation. Solvation talks about how water dissolves a substance. And the big factor here is the positives and the negatives, especially if we're dissolving substances that are ionic, which are all the way positive and negative, or also polar covalent. Let's take a closer zoom in on what's happening here. Consider dissolving table salt, sodium chloride. In this picture, we have my sodium ions being the little blue ones with a positive sign, and the negative chlorine ions are in green. We can see that the water molecules are attracted to these positive and negative bits in the ionic sodium chloride. The positive end of the water molecule, the hydrogens, will spin and orient themselves to kind of be attracted to the green chloride ions. Now, just one of them doesn't have an effect, but after a while, several of them can actually overcome the attraction chlorine has for the sodiums and pull them away. And when it does this, it gets surrounded by a shell of water molecules, and we call that little cage a hydration shell. So that chlorine is now surrounded in a little cage of water molecules, and because of that, it can't get back to the sodiums. Now, at the same time, the sodium is attracting the negative end of the water molecules. So if you're wondering which part of the water molecule is surrounding the sodium, it's the negative end, the oxygens, because opposite charges attract. And again, we're going to find that we're going to get surrounded by a hydration shell. So ionic substances dissolve in this way. Ion by ion, they get pulled apart, surrounded in little cages of water molecules, and that keeps them from being able to get back together. This explains why you can't see the separate parts in a solution. We're talking about dissolving individual ions from each other. Now, in the case of a polar molecule, one that wouldn't separate into ions, the water will still form cages around individual molecules. Again, our molecules are going to be too small to see with the naked eye. Individual molecules are very, very tiny. We remember this from our unit on stoichiometry, where we learned that there was 6.02 times 10 to the 23rd particles in any mole of a substance. So you can imagine how tiny they are. It also explains why you can't just filter out the bits in a solution. We're talking about particles that are just too tiny to be separated by filtering. So if I want to know then, when we understand now about why things dissolve, how water forms little shells around individual ions or individual molecules, we kind of need to know why some things dissolve and others don't. And the general rule, and the most obvious one we can lean to, is like dissolves like. Now, when I'm talking about like, what I'm referring to is the polarity. Water, which is a polar molecule, will dissolve anything that's like it. So anything that's polar, or actually in the case of water, also anything that's ionic. Because if there's positive and negative sides or positive and negative ions, water can form cages around it. Water is not going to be able to dissolve nonpolar things. Remember polarities and electronegativities? We take a look at any bond and take a look at their electronegativities and subtract the difference in strength. We come up with a number, and that number allows us to know whether the bond being formed is polar, nonpolar, or ionic. Nonpolar substances that don't have positive and negative ends will not dissolve in water. They tend to form precipitates. Things that cannot dissolve in water are called insoluble. In means will not. Soluble talks about dissolving in water or in what other substance. But for grade 11, we're going to use water. So organic substances don't dissolve well in water, which explains why when you get a grass stain or an oil stain or even a blood stain in your clothes, it doesn't wash out well. If I want to dissolve something in water, it has to be either polar covalent or ionic. These substances are soluble in water. Soluble means they will dissolve. Substances that will dissolve in water are said to be aqueous. The symbol AQ just tells us that the substance that you're using has been dissolved in water. Now, when I make solutions, there are 4 factors I want to consider. These 4 factors either affect how fast a substance dissolves in water, in other words, its rate, or how much of the substance dissolves in water. The how much is called the substance's solubility. Add that word into your notes. Or, in some cases, both. So as we consider each of these 4 points separately, I want you to consider how fast, how much, or both. The first one is agitation. Agitation means that we're stirring it or shaking it or somehow moving the particles around. Now this affects how fast the substance dissolves, but not how much. Stirring or agitating, shaking in any way, what it does is it brings the solute particles, the parts that are getting dissolved, closer to the solvent particles. It allows the water, for example, to reach each molecule of salt more quickly. But it doesn't change the ratio of salt to water. So we're not going to get more dissolving. We won't increase our solubility, but we will dissolve things faster. So if you're trying to dissolve sugar in your coffee in the morning, stirring it helps speed up the process. Temperature. If I heat up a substance, I can quite often dissolve more. We know this about the sugar in the coffee analogy. Hot coffee dissolves a lot more sugar than cold coffee will. But this is only true for solids dissolving in liquids. When it comes to gases dissolving in liquids, the opposite is true. When we try to dissolve anything in a liquid, what happens is the water molecules spread out a little bit and they move faster. So this also would increase the rate of dissolving. So temperature when we're dissolving a solid would affect both how fast and how much. As the water molecules move quicker and spread out, they will be able to have less water molecules hold each solute molecule in the hydration shell cage. Picture a game of keep away where you've got groups of kids with their arms out and you're trying to keep somebody in the middle of a little group. If you're not really involved in the game and you're kind of feeling bored, you just walk. Well, it might take several of you to make a cage tight enough to hold a solute molecule in place, the person in the middle. I've drawn a quick little diagram here of a group of water molecules holding this little solute particle in the middle. In cooler temperatures, this particle being a solid, moving slow as solids do, might be looking for a way to get out to join up with its oppositely charged particle, but it can't because the water has formed a cage around it. Water is a liquid, so it can move faster than the solute can as it is. As I heat the water up, though, what happens is the water molecules will start to spread apart. Now, we might imagine that this solid molecule could try to escape, but what we notice is that the water can still move faster than the solid can because liquids have more kinetic energy than solids do. So now it might only take 2 water molecules to keep this solid caged, and so we have more water molecules available to dissolve other solids. We can see the problem, however, forming if I was trying to dissolve a gas, because gases, of course, can move faster than liquids. So when a gas starts moving faster as we heat it up, it would see this open hole and boom, would be gone right away. Now, this is part of the problem with global warming, because as our oceans heat up, warm water can hold less dissolved gas than cold water can, and so fish that are used to having a certain level of oxygen will notice that the amount of oxygen available for them to breathe would be going down and they'd be getting stressed. So for temperature, as we heat it up, we can dissolve more of a solid but less of a gas. You can see the same information on graphs that talk about the solubility. Now, this is solubility, how much can dissolve. Please don't mix up the word solubility with how fast. Solubility is how much. You notice that these lines go up, more grams of each of these salts. These are all salts, and salts are always solid at room temperature. These salts can all dissolve more as we heat the temperature up. Okay, with the exception, of course, of cerium sulfate. There's always exceptions to the rule, and we'll talk about exceptions coming up in our next lesson. But as the general rule, as our temperature increased, the amount of salt that could dissolve increased. This graphic shows gases dissolving, and you'll notice that gases will go down in solubility. Less grams are able to dissolve as the temperature gets warmer. Particle size is our next one. Now, when I'm talking about particle size, what I'm talking about is the chunks that we're throwing into the water. I'm not talking about the size of the molecules. Think, for example, about powdered sugar and granular sugar. Like you might put powdered sugar would be like icing sugar, and granular sugar could be more like a teaspoon of sugar you'd put in your coffee, or a sugar cube. So what size of particle am I putting into my water? Well, the smaller the particle, the faster they dissolve. And of course, that's because the water can get to each molecule to cage it up more quickly. But this doesn't affect how much can dissolve. We are still not changing how many waters it takes to surround each solute molecule. We can think of the same analogy when you're trying to burn a log and you're thinking about, wanting to be able to get to it. A log itself has less surface area than if I cut the same log into kindling. When I cut it into kindling, I've exposed all those interior surfaces to the flame, and you'll notice that the fire burns much faster. It's the same with the sugar. If we grind it up or crush something, what we've done is created more surfaces for the water to attack each molecule, and so the dissolving process happens much better. So when we think about particle size, it goes hand in hand with surface area. The smaller the particles, the more surface area you have. So pay attention to the words that we use with those ones. Finally, pressure. Now, pressure affects only gases. We know from our previous units that pressure can't affect liquids and solids. But pressure affects how much when gases dissolve. Pressure is a big deal for dissolved gases, especially if you're a scuba diver. Scuba divers who dive really deep have lots of pressure on their body, so their blood will dissolve a lot more gas in it than normally. If a scuba diver tries to come back up to the surface too quickly, well, then the pressure that's on their blood drops, and all those excess dissolved gases have to go somewhere, and since the body can only breathe them out at a certain rate, what can happen is they can form bubbles, and essentially the blood starts to boil because we've dropped the pressure too quickly. So that boiling of the blood is the bends, and it's very, very painful, and it can be deadly. Now, remember, we can change the boiling point of any liquid by lowering the pressure, because any liquid will have a certain amount of dissolved gases in it. The lower the pressure, the more readily they form the gas phase. The particles can move apart. So pressure affects solubility, how much, and it's a direct relationship. More pressure means gases will be more soluble. We can dissolve more. If there's less pressure, gases are less soluble. We will dissolve less. Now, when we talk about solubility itself, we're talking about that maximum amounts that can be dissolved. So if there's a maximum amount, that's the point where we can't dissolve anymore. And how can we tell? Well, if I have an unsaturated solution, that means that there's room to dissolve more solute. If I have an unsaturated solution, as you can see in this first test tube here, you will notice that if I go and try to add more solute into the test tube, it'll just dissolve. So that would be a way that we would know it was unsaturated. We could still dissolve more. I couldn't see anything sitting on the bottom, so clearly there was room for us dissolving more. It's unsaturated. At the point that a solution is saturated, if I try to put more solute crystals into the solution, they'll just hit the bottom and form a precipitate. A saturated solution is defined as one that is holding the maximum amount of solute that it can hold at that temperature. Now, it's always temperature dependent. A saturated solution has hit the solubility for that salt. We've dissolved as much as we can per given amount of water. Remember, there's always two measurements. What then is a supersaturated solution? A supersaturated solution is defined as a solution that is holding more crystals than it should be able to. It's holding more than the maximum at that temperature. It's hard to picture sometimes how something can hold more than its maximum. If you're holding it, how's that not the new maximum? Well, it's a trick. In a supersaturated solution, what we do is we plot these extra crystals kind of really precariously suspended in the water. The water is not actually forming proper cages around them. It's just, they're sort of balanced in there. And I know that a solution is supersaturated because if I drop in just one crystal, many form on the bottom. As opposed to a saturated solution, if I drop in one crystal forms on the bottom. If I drop in a supersaturated solution, one crystal, many will form on the bottom. Supersaturated solutions are very unstable. Let's take a look at a quick example. So the solution you see on your screen here is supersaturated, and you will see that if I pour in just one crystal, there's the one crystal in, all of a sudden many crystals start to precipitate out. I've included links here to a couple of videos that you can look at, and I'll post them below the video so you can go back and watch them in their entirety after this one. Now, a couple of more terms I want to talk about with this lesson. Miscible and immiscible are words you're going to read in our textbook, and they talk about liquid-liquid systems. So if I'm dissolving one liquid into another, I often think about a simple liquid-liquid system like rum and Coke. It's a common little drink that many people have, and both of them are liquids. And if you pour one shot of rum into a big glass of Coca-Cola, then you would say that probably you'd say the Coke was the solvent, it was doing the dissolving, and the rum was the solute, it got dissolved. But this same system will work if you pour equal amounts, one shot of each, or if you reverse the quantity, although I wouldn't recommend you do so, and pour one shot of Coke into a whole glass of rum. Because it's hard to say which is the solvent and which is solute in liquid-liquid systems, we tend to say that two liquids are miscible if they can dissolve in each other. And if they cannot dissolve in each other, they're immiscible. Oil and water is a good example. Now, we can quite often shake up oil and water, and we can get a foamy-looking substance. That's called an emulsion. So we call it an emulsion then because emulsions will separate if left to stand. They temporarily can have symptoms that look like a solution, but in fact they're not. Now, our way of practicing this is all out of the textbook for now. What I want you guys to do is go and do some reading in your textbook on pages 49 to 495, and there's a good amount of questions there. We've got about 8 or 9 questions for you to practice working on. Also, there are a couple of worksheets that I can get you guys to work on in your textbook. In your workbook. So in your workbooks, we've got on pages 10, 11, and 12 a bunch of questions that are going to help you practice understanding what we've talked about in terms of how solutions are made and what affects how much will dissolve. Pages 13 and 14 include a lab, and I quite often would have you work on these questions while you were doing the lab, and obviously we can't do a lab from home. But the questions 3 to 7 on page 13, and then the questions on page 14 can be done based just on what we've talked about here, the 2 films that I'm going to let you watch here that will be linked below the video, and also what you've read in your notes in the textbook. So they will do a really good job of kind of talking about everything that we've discussed in this video. So that's what I'm going to get you guys to work on for a day or two to understand thoroughly the theory behind how solutions form and the factors that affect how much will form and how fast they form.